Okay, guys, Mr. Santiago again. In the next video of the series of Unit 11, Kinetics and Equilibrium. So hopefully you've already watched the first two videos. Now we're going to move on to equilibrium and we'll talk about what that means. So in a chemical reaction, the equilibrium state is where the concentrations of the reactants and products remain constant. In other words, even though these guys are reacting to produce these guys, and notice the double arrow, which means it's a reversible reaction. These guys are also reacting to produce these guys. They're both reacting at the same time in both directions. But if these guys are reacting more quickly to create this versus what's happening in the other direction, then we say overall the reaction is moving forward to the right. If these guys are reacting at a higher rate to produce this versus what's going on the other direction, then we say the reaction overall is moving in the reverse direction, right, leftward direction. All right, and so this is a reversible reaction noted by the double arrows. Sometimes you'll see those double arrows written a certain way. Let's just say, sometimes they show it like this, where it's just a kind of full double arrows. That's fine, it means the same exact thing as this. These are just two half arrows. Sometimes you'll just see a double-headed arrow, which is also the same thing. Right, you see it looks like this, and that all means the same thing. It just means it's a reversible reaction. So you have these guys reacting and creating products over here. You got these guys acting like reactants to create products over here, and they're both, and the reaction is going both directions. All right, so whichever direction is happening at a faster rate, right, that will determine the overall direction of the reaction. All right, if they're both at the same rate, then we say we are at chemical equilibrium. Okay. All right, so it looks like the reaction is finished when that happens, but the molecules are still going. Right, these guys are still reacting to make these guys. These guys are still reacting to make these guys. But if they're occurring at the same exact rate, then we are at equilibrium, and it kind of looks like nothing's happening. Okay, and so that's equilibrium, and all reactions all reversible reactions head towards equilibrium. They always move in that direction. Okay, all right, now to look at this mathematically, we use the reaction quotient. We solve for the reaction quotient, which is really nothing more than the products over the reactants, the ratio of the products over the reactants. So you can think of the top, the numerator, these guys, these are the products over the reactants. Okay, and it's the concentration of the products over concentration of reactants. Now notice the exponents. The exponents here, if you noticed on the last slide, are the coefficients in the chemical equation, right? So you can see here the little a, that becomes the coefficient of reactant A. So going back to this, here's reactant A, right? It's a reactant, it's on the denominator. So here's the concentration of reactant A with the little lowercase a up here representing the order, right? Or basically the mole ratio, right? This is basically going to, your little lowercase letters are representing your mole ratios, right? And so that's essentially what you're putting up here as your exponents, okay? Okay, so here we go. We have your products divided by your reactants. It will always be this way. This is how you want to calculate these. And given some values, you can plug everything in and find out what your reaction quotient is, right? See what that ratio is of products versus reactants. Okay, now as a chemical reaction proceeds or progresses, the value of Q will change. And the reason for that is because as the reaction is going on, you have stuff going on. In other words, let's just say we're moving overall in the forward direction. Well, if we're moving in the forward direction, that means you're using up A and B more quickly than C and D. So you're using up A and B to make C and D. So your products overall are getting greater. The concentrations of those guys are getting greater. The concentrations of these guys are being used up, so they're getting less. So therefore, when you look at the mathematical ratio, this will be changing. Your value of Q will change. And it will continue to change as the reaction progresses until you reach equilibrium, right? Because at equilibrium, we already said the rate of the forward and the rate of the reverse reactions are going to be exactly the same. Therefore, the concentrations will remain the same. They won't change. And so that's what's happening here. So that's what Q is, a reaction quotient. Okay, we call it that, and we use the reaction quotient anytime we want to make this calculation, unless we know it's at equilibrium. If we know we are at equilibrium, then we don't use Q anymore. We still set this up the same way, but we don't use Q anymore. We use K instead. But anyway, let's go ahead and get some practice setting up this reaction quotient expression. So here we have a couple of examples, and they want us to write the reaction quotient for the following. So we have, let's take a look at this first one over here. Now, again, you're always going to set it up products over reactants with the coefficients going up as exponents, okay? So go ahead and pause the video, see if you can figure that out based on our last example and see what you come up with. Now, if you went ahead and gave it a shot, let's take a look at what our answers are going to look like. All right, so here we go. We have QC equal to NO2 to the second power. So again, this 2 right here, let me change the color on this. So this 2 right here, right, where did it come from? It came from there, okay? And then this, there's an invisible 1 here, right? So therefore, there's an invisible 1 down there. All right, so that's how you would set up your reaction quotient expression, okay? And if you have some values, right, you can plug them in and just solve. Down here, we have the same kind of situation. Here, look at, we have different coefficients. We have it's a 3 to 1 to 2 ratio here. Now let's take a look at, it's always products over reactants, so let's take a look at the product side. So that's going to give us concentration of ammonia, right, with 2 as its exponent, divided by those on the reactant side. So on the reactant side, we have the concentration of diatomic hydrogen and nitrogen. The hydrogen, however, we need to cube that because of the coefficient 3 here. So the hydrogen gets cubed, and the diatomic nitrogen, because there's an invisible 1 here, there's an invisible 1 there. So this would be the overall expression, and this is how we would write it for this type of situation. Okay, now as mentioned earlier, if we know we're at equilibrium, well then we replace Q with K. Okay, now if you notice Q, we have QC. C just represents concentration. So let's not, I don't want that to trip you up. If you see, well, C means concentration, and therefore Kc means concentration also. And later on, we'll talk about pressure. We don't only solve for these types of situations using concentration. Sometimes we use partial pressure to solve equations like this. It's all set up the same way, and we'll look at some examples of that shortly. But in that case, we would put QP here if we were dealing with partial pressure. And that's all that means. So don't let the little subscript throw you for a loop there. All right, in any case, this is actually a mistake. So QEQ, well, actually it's not a mistake. This is correct. But when Q is at equilibrium, all right, so in other words, when the reaction finally gets to its equilibrium point, whatever that Q value is, we're going to replace it and use K instead. K, capital K specifically. Capital K is what we use to represent the equilibrium constant. All right, now if it's Kc, that means again we're dealing with concentration values. If it were Kp, for example, then we would be dealing with partial pressure. Still products over reactants, but it would be dealing with partial pressure. Now sometimes you'll see Keq, just like you see here. Keq is just a generic overall catch-all subscript that we can use, but still, your K is K. It means the same thing. It's the equilibrium constant. Okay, but again, we only use K. K, basically, when you use K, it tells us that the reaction is at equilibrium. That is the value, right? That's your quotient. That's your answer for this ratio when you're at equilibrium. All right, so let's take a look at this example. Now, I'm going to actually start with the bottom example first. I think it might make a little bit more sense. So when Q or K equals 1, that means that your products and reactants are equal. Because remember, this is your products. Hold on, here we go. All right, so your products divided by your reactants, right? That's what this whole setup is all about. So think about it. If your product concentrations are equal to your reactant concentrations, well, if these are equal, well then what does that equal? That equals 1. So that's what we're talking about here. All right, if Q or K, either one, equals 1, then the reactant and product concentrations are equal. Okay. Now, if your Q or K is, let's just go work our way up. If Q or K is less than 1, well, think about what this ratio has to look like to be less than 1. That means your denominator would need to be greater than your numerator in order for that to be less than 1, right? Like, for example, half, 0.5, 1 over 2, right? Your denominator has to be greater than your numerator in order for K to be less than 1. So therefore, your reactant concentrations will be greater than your product concentrations, all right, in that specific case. Now up here, if your Q or K is greater than 1, well, the only way that this answer here can be greater than 1 if your numerator is greater than your denominator, which means your product concentrations, the total product concentrations are going to be greater than your total reactant concentrations. Okay, and that's the only way you're going to get anything greater than 1. Okay, so that's what this is referring to right here. Now, why do we care about this? Well, we care about this because when we solve for Q, and if we solve for Q and then compare it to a known value of K, we can decide or figure out which way that reaction needs to go, left or right, in order to reach equilibrium. And then you'll see some more examples of that as we go further on. All right, so let's talk about the difference between homogeneous equilibria and heterogeneous equilibria. It's kind of similar like with when we talked about homogeneous and heterogeneous catalysts. Same idea. We're looking at the state, right? The phases that these substances are in. So homogeneous equilibria is when all substances are in the same state, meaning they're all gases or they're all aqueous, right? That's homogeneous equilibria. Heterogeneous equilibria is when the substances are in different states. So you might have, gases, being produced as a product, but you're starting with aqueous solutions or something like that. That's called heterogeneous equilibria, all right? Now, one thing about these equations that we write, the Q or K equations, products over reactants, one thing about these, we never ever include solids or pure liquids, okay? We never ever include those in the mathematical equations because those, you don't really look at those as concentrations, and if you do look at them as concentrations, they don't change. You can't change those. They're pure substances. So there's no way that we can track a change of concentration in any way. So it doesn't make any sense really to include those in the expression. Okay, so let's take a look at let's take a look at this last bullet right here. This only applies to pure solids and liquids, like we just said. We don't include them in the equilibrium expressions. It does not apply, however, to aqueous solutions. So pure liquids, all right? That's not the same as aqueous, right? Aqueous means you have something dissolved in water, something mixed into water. So that's different than pure liquids, okay? And then, of course, gases, right? Gases, you can have different concentrations of gases. But with gases, it's actually easier to deal with partial pressure. We'll talk about that when that time comes. So let's take a look at sample problem 5. Write the equilibrium expression for each of the following. So let's take a look at both of these. Again, you can pause the video if you think you can set this up. For those of you who need a little bit more guidance, well, you're going to set it up the same way we did before, products over the reactants, with the coefficients becoming the exponents for each. However, keep track of the phases here. Take a look at these phases here, right? We already said in the last slide, solids and pure liquids don't get included in the expression. So this is a solid, so we're going to ignore this. This is a solid, we're going to ignore this. So essentially, our entire expression is going to be created based on this product alone. So you can think of this, you can ignore this the way I did here, but you can also think of it as equaling 1, right? You can just think of it that way, okay? And then, of course, over here, down here, same thing. The solids, we can ignore that or think of it as equaling 1, and then you have your products over here. So looking at the answers for these, we have this situation. So here are your products, but again, we're ignoring this one, right? Or thinking it as 1. So 1 times the concentration of O2 cubed, right, is just O2 cubed, right? So there's the products. Now the reactant in the denominator, the reactants, again, you can just ignore that or think of it as 1. So it's this over 1, right? So therefore, overall, your end result is this. This is your equilibrium expression, okay? Then for part B, it's the same thing. We're going to ignore this or think of it as 1, and then we're going to have the products. So here are the products, right? The 2 here becomes the 2 here. And then this, we can think of it as 1, so we put it over 1. Overall, your end result is this right here. All right, so that's basically it. That's how we set everything up. Now, we're going to go a little bit deeper into these equations, and we're going to start solving problems with these equations, but we're going to do that a little bit later. I just wanted to introduce this to you now so that when we talk about our next principle, the Châtelier's principle, you'll understand why things are shifting right, shifting left, and it's all, again, it's to maintain this ratio. Okay, so in other words, this value is a ratio of products and reactants. To maintain this ratio, if I change the concentration manually, if I just go ahead and change the concentrations of these guys, the reaction is going to shift one way or the other in order to reach equilibrium again. And that equilibrium is going to have to equal the same thing that it originally did with the original starting amounts. And you'll see how that plays out later on. All right, so let's talk about Kc and Kp. Now, Kc, again, C means concentration. P represents pressure, right? So we deal with partial pressures often with gases because it's easier. And it's going to work exactly the same way. Let's take a look at this carbon dioxide plus solid carbon example coming together to create carbon monoxide. Well, if they're asking us what is the Kp of the above reaction, if at equilibrium the partial pressure of carbon monoxide is 0.598 atmospheres and the partial pressure of carbon dioxide is 0.159 atmospheres, well, you're going to set everything up the same way, right? Products over reactants, all right? But we're going to ignore that because it's a solid. So this is the way you would set that up, right? So your products over reactants, same way you do earlier, except instead of concentration, right, with using the brackets, we're going to use capital P representing partial pressure. So the partial pressure of carbon monoxide squared, right, that came from this right here. And then we have the partial pressure of carbon dioxide, right, again, and the invisible one as a coefficient is an invisible one as an exponent here. So this is how we set it up. Now all we have to do is plug in the numbers, which we did right here, do the math in the calculator, and then we get our answer. Now K doesn't have any units. We don't use any units for K, so don't worry about any units here. Okay. Now that's different from lowercase k, the rate constant earlier when we talked about rate laws. That little k has units, so you got to make sure you pay attention to that. But the capital K here for equilibrium, we don't use units for that. All right, so here's Le Châtelier's principle. Oftentimes we just abbreviate, we kind of shorten it and we say Le Chat's principle. All right, but Le Châtelier's principle is officially what it's called. Now, what is this principle? This principle basically states that when your equilibrium is disturbed, let's just say you have a reaction and it's at equilibrium. Well, once it's at equilibrium, it's going to stay at equilibrium unless you do something to it, right? If something, or unless it's affected by something. So if, the concentration of the reactants and or products are increased or decreased, right? Well, that's going to change things and it's going to have to reestablish equilibrium again. So that's really what this principle states, that anytime equilibrium is disturbed, it's going to reestablish itself by going either in the forward or the reverse direction to reestablish equilibrium. Okay, so the equilibrium position shifts in a way that reduces the changes in concentration. In other words, if you're adding more reactants to something that's already at equilibrium, you're adding more reactants, well, now you have too many reactants. So therefore, it's going to have to shift to the right in the forward direction to get rid of use up some of those reactants, right, to reestablish equilibrium again. And that's basically what we're talking about here. All right, so let's take a look at these bullet points. If you add a reactant, there will be too many reactants and a forward shift will occur. You know what, I'm just going to be a little bit thorough here, and I'm going to create some, just something here. Let's, oops, I don't like that. Let's do this. All right. One of these days, I'm going to get myself a stylus. Just don't have one right now. Okay, so here we go. We have, let's say A plus B creates AB, while AB breaks down to create A plus B. So it's a reversible reaction. They're both happening at the same time, but if you have more of this happening at a faster rate versus this breaking down at a slower rate, then overall you go into the right. If this is breaking down faster than these guys are building up, well then overall we say we're going in the reverse direction. If they're both happening at the exact same rate, then we say we are at equilibrium, and it's going to stay at equilibrium until something changes. Now, let's change something. Let's add a reactant. Now, if we add A or add B, it doesn't matter which one. If we add A, let's say for example, well then you're going to have too much of A. So in order to reach equilibrium again, we're going to have to use up some of that A because we have too much, which means overall we're going to have to shift, the reaction is going to shift and establish a new equilibrium position as it trends to the right. As the reaction shifts more in the forward direction, we say we have a new equilibrium position to the right. And that's because we had to use up some of A to make this to reestablish equilibrium. Now, if we add a product, let's just say we add some AB here, well, now we have too much AB. So if we have too much of this, we have to use this up, right, to go in this direction, and we say that the reaction shifts to the left. And so that would consume more of the product, right, to create more of this to reestablish equilibrium. All right, now let's take a look at volume. Let's say we're dealing with gases here, right? Let's take a look at volume. When you decrease the volume, making it smaller, a shift will occur in the direction where there are fewest gas molecules. All right, so if these are all gases, that means you have a 1 here, a 1 here, and a 1 here, right? The way I wrote it, you have an invisible 1 as a coefficient here, a 1, and a 1. So overall, on the reactant side, you have a total of 2, right? 2 moles of gas molecules. Here, you have a total of just the invisible 1 here, so you have a total of 1. So if I decrease the volume in this situation, the reaction is going to shift to the right because it's going to shift to the direction where there are fewer gas molecules. So since you have a 1 and a 1, which equal a total of 2, and you only have a 1 here, well, that's fewer than the total over here. So therefore, it's going to shift to in the direction where there are fewest gas molecules. Okay, so that's what we're talking about here. Now, the reverse is also true. If you increase the volume, let's just say, well, then it would shift in the opposite direction. It would shift in a direction where there are more gas molecules. So just keep that. It doesn't state that here, but just maybe make a separate note of that. Okay. All right. Now, if you add a catalyst, if you remember way back when we talked about catalysts, it seems like it was way a long time ago. Catalysts increase the rate of reactions in both directions. So even though a catalyst will speed up a reaction, it's going to speed it up in the forward and the reverse direction. So all a catalyst really does, it doesn't cause an overall shift left or right. It basically speeds up both directions at the same time, helping this reaction reach equilibrium more quickly. And then last bullet point, temperature is the only change that will affect the value of K. Okay, so K does not change under any certain, in other words, if you're increasing the concentration of something, decreasing the concentration of something, increasing, decreasing the volume, it doesn't matter. K still stays the same. Remember, K is equal to your product concentrations over your reactant concentrations. Okay, so this is always going to be constant no matter what. So if I'm increasing the concentration of this, it's going to shift to the right. In other words, I'm going to have too much reactants. That number is going to be too big to satisfy what K is supposed to be, so therefore the reaction is going to shift to the right to use up some of those reactants to make product. This number gets bigger, that number gets smaller, and then K is back to where it's supposed to be. So let's just say K is equal to 0.5, let's say. I want to make sure there we go. Let's say K is equal to 0.5. It's still the same situation. You have, all right? So let me just get this stuff out of the way here. Need some of it. All right, so let's just say K is equal to 0.5. Well, think about it. If you have, let's just say you have, I'm just going to make this up. You have 1 molar of the products. You have a total of 2 molar, 2 moles per liter of reactants. Okay, so if this is the case, well, K is a constant, like we said. That means it's not changing, all right, other than the effective temperature, which we'll talk about later. So if K is a constant and you increase products, for example, let's say we increase AB, well, now if you increase the products, you're not going to have half anymore. So this reaction has to shift in a way to maintain that value of half, or 0.5. So the only way to maintain that value, so if I have too much of this, let's just say we increase this to, 2 molar, well, now that equals 1. That's too much. So what's going to have to happen? The reaction is going to have to shift in this direction again to use up some of those products, to bring this number down and bring that number back up in order to create 0.5 again. Okay, and that's the general idea behind why these reactions shift. Okay, let's move on. So let's take a look at equilibrium, what will happen if the concentration of diatomic nitrogen is increased. So here's diatomic nitrogen and hydrogen creating ammonia. If we increase the diatomic nitrogen concentration, so we're increasing this, okay, think about what would happen. All right, pause the video if you need to think about this for a second. So we're increasing the concentration of this, which means we're going to have too much of it. If we're going to have too much of it, we need to use up some of it to make this. So in other words, we're going to have to shift to the right. So that'll use up some of the nitrogen, create some more product to keep your constant K value at the correct ratio. Okay, and that's what will happen until new equilibrium is reached, new equilibrium position. All right. So because there are more nitrogen molecules, let's take a look at these bullet points. Because there are more nitrogen molecules, there will be more collisions, and therefore there will be more ammonia produced. So think about it in that way. All the way back when we talked about rates of reaction, or factors that affect rates of reactions. What happens if you increase the concentration of something? Well, now you have more particles, more colliding, more banging against each other, and therefore faster reactions. If you increase and these guys are banging and colliding into each other at a faster rate, that's going to push the reaction in this direction because these guys are going to react more quickly than they normally would have, and it's going to push it in this direction. Now, the rate of the forward reaction is increased. We just said that. As more ammonia is produced, the reverse reaction will also speed up, and the system will reach a new equilibrium position. Okay, and so the equilibrium overall, we say, shifts to the right. So in other words, this reaction needs to shift to the right to establish equilibrium again. All right, so we establish a new equilibrium position by shifting to the right. So even though the equilibrium shifts to the right, the equilibrium constant K stays the same, and that was kind of the example that we looked at over here. You know, when something is changed, right, this isn't going to work. You have to make sure K stays the same. So this is going to go down, right, in concentration. The reaction shifts left in this case. Products go down, get used up, as these guys are going to build up again in order for 0.5 to be reached again, that correct ratio. And that's what we mean there. K must stay the same. All right, sample problem 6. Determine whether the equilibrium position will shift left or right for the following. So if we increase the concentration of ammonia here, all right, well, if we increase this, right, we're going to have too much of this. Again, pause the video, try to figure this out. If you need, but if you can't figure it out, or if you want to check your answers, then, you know, start the video again. So in this particular case, right, we have too much NH3, we're going to have to shift left. Now, in this case down here, now don't get confused by this. HB is not an element on the periodic table. It's actually standing for a biochemical molecule called hemoglobin, and that's found in your blood. It's what carries iron, and iron is what attracts the oxygen. So hemoglobin is responsible for carrying oxygen in your blood. So if we decrease the oxygen, here's a chemical reaction. This is a chemical reaction in general that occurs when your blood picks up oxygen or releases oxygen. When O2 is decreased, there's O2. When it's decreased, well, now, since we decreased it, we don't have enough of it. So in order to reestablish equilibrium, right, you got to shift left. That's the only way you're going to be able to reestablish equilibrium. You've just taken away some O2, right? You decreased the O2. You took some away. So now you're short O2, which means you've got to make more of it. So it's going to shift this way to make more to reestablish equilibrium. Okay? And then what if a catalyst was added to the above reaction? Well, again, catalysts speed up reactions, but they would speed them up in both directions. Okay, so then therefore there would be no shift. And that's what we're looking at here in the answers. All right, let's take a look at C, D, and E. Again, pause the video, try it out, and then go ahead and come back to the video and see how you did. So for part C, we have the concentration of carbon monoxide being decreased. So here's carbon monoxide. If we take some away, that means we don't have enough, which means we need to produce more of it, which means you're going to have a shift to the right. The volume of the container is decreased. All right, well, don't forget our rules with volume. We have to look at how many molecules of gases there are on both sides, because when you decrease the volume, it's going to shift to the location where there are fewer gas molecules. So in this particular case, we don't really care about, well, this is a solid, so we're not going to look at that. That's a solid, we're not going to look at that. There's your gas. So we have an invisible one here, nothing over here. So we have 1 on the product side 0 gas molecules on the reactant side. So the fewer location would be on the left. So therefore, the reaction will shift left. It will shift to where there are fewer gas molecules. That's what happens when you lower or reduce the volume of the container. And then, of course, the opposite would be true. So if we increase the volume of the container, as an E over here, then you're going to shift to the location where there are more gas molecules. So we have an invisible 1 here. We have our 3 here. So there's 4 total. And here we have 2. So 2 is less than 4. 4 is greater than 2. So because we're increasing the volume, it's going to shift left to where there are more gas molecules because we're doing the opposite versus what we did over here. We're increasing the volume. Okay, and that's what we have over here. Okay, so let's talk about temperature and how temperature affects the shifting or equilibrium position. Now we have what are called exo and endothermic reactions. Exothermic reactions are reactions that release heat. All right, so these reactants come together. When they react, they release heat. So if this was in a solution, for example, some aqueous solution, it's not, these are gases, but let's just pretend this was in an aqueous solution, in a cup. Well, as these guys are reacting, they would be producing heat, right? This annotated here by the 92 kilojoules of heat energy over here on the right side. So if you're holding a cup and this reaction is going on and this thing's producing heat, well, that cup's going to feel hot because it's producing that heat as a product, and you can feel it. An endothermic reaction is one that actually absorbs heat, and so it actually, that cup of solution would feel cold if that were happening in your cup. In any case, let's start with the exothermic. We have an endothermic reaction. Now, if you have 92 kilojoules of heat being produced, based on what we have here in this reaction, well, it's going to go on the product side. We're going to write down the heat energy, right, or the 92 kilojoules on the product side of the reaction because that is a product. It's being produced. So therefore, it's over here. So the reason we would do that is simply because now you can heat this up, you can cool it down to try to get the reaction to go right or left. If I heat this up, now this is going to act just like concentration does. If I add heat, if I heat this up, right? If I heat all this up, this whole system, well, because it heats on the product side, and I add more heat to it, well, now I have too much heat. Well, how is it going to reduce the heat? Well, it's going to have to shift left in order to reduce the heat, and that's what we're talking about over here. It shifts left, all right? So again, it works exactly the same way as you would think about, when you think about concentrations. You increase the concentration on one side, it's going to shift away to the opposite direction, use it up. If I were to decrease the heat, right, cool it down, right, put this whole thing in a refrigerator and remove heat, well, now there's not enough heat, so then it would shift right in that case, if that were what we were doing. Okay, and then endothermic reactions, like I mentioned, are the opposite. They absorb heat. They don't produce heat. They absorb it. So this is something that you would put on the reactant side. So here is your heat energy shown on the reactant side of the chemical equation. Okay, now, if heat were added in this case, right, again, think of it like concentration. If I add heat, I have too much of it on the reactant side, which means I need to use some of it up, right, and it's going to shift that way, use some of it up. If I were to cool it down, right, then it would shift to the left, right, because I wouldn't have enough heat, and it would have to shift to the left to create more heat. All right, so that's your difference between endo and exothermic reactions. So let's take a look at sample problem 7. Now, they gave us the chemical equation, and notice what they did. They put heat on the product side. So A, is this reaction exothermic or endothermic? Okay, again, pause the video if you want, take some time, think about this, and then come back. So is this reaction exothermic or endothermic? Well, since heat is on the product side, that means heat's being produced, and if heat's being produced, we have an exothermic reaction. So which way would the reaction shift is if heat is removed? So if you're taking away heat, right, that means you're not going to have enough of it. You have to make more of it, which means the reaction would shift to the right. Okay? All right, we're going to skip this. We're not going to skip it, actually. We're going to get to this in the next video. So I guess that'll be it for today. So again, keep pushing forward. I know these are unprecedented times, but nonetheless, you know, we'll get through it and it'll be all good. So until next time, guys, have a good day.